little short. So let's make use of my, oh no, stink. Seriously. Oh. Whew, I thought for a second there was no HDMI cord here. But it's okay, there is one. It exists. All right. So yeah, I'm probably not going to upload that last little snippet where the other professor walked in, but we did figure out that E needed a, whatchamacallit, an index. All right, let's see here. All right, so two matrices are equal if and only if their components match. Let me see if I'm gonna turn off the lighting in here just for the sake of making that show up better on the camera. Zoom in a bit. Maybe a bit more. All right, well, hopefully that'll work. Yeah, so these are my, what did we say, 2019 linear algebra notes?
I read this chapter.
Oh, cool. So is there anything you had a question about specifically, or?
I don't think so.
Okay, cool. All right, well, zero matrix, there, we talked about this. So these notes, I tried to do it like over a ring, right? Which isn't really much of a difference, it's a difference without a distinction almost. I've been watching a lot of Calvinism videos lately. This Leighton Flowers guy, he likes to talk about, it's a distinction without a difference. It's like, he's kind of a troll, I don't know. Like, do you know who I'm talking about?
Not the distinction.
Oh, okay. Do you know who Leighton Flowers is? Okay, that's cool. All right, so yeah, matrix multiplication, we got that. Properties of matrix multiplication. I should have looked at my index. My apologies. So here's the, these are all the things we talked about. There's a grand collection. Now that right there is important. This one, that one is important because that basically shows you that the matrix units are they're a generating set, they're a spanning set for the set of all matrices, right? So and since we can also prove that they're linearly independent, that shows you that the m by n matrices form an mn dimensional vector space over the field, right? That's of course interesting. There's so much to say about matrix algebra that extends past, just linear algebra. Let's see here. Define exponents. You know about symmetric and anisymmetric matrices? Yeah?
When transpose is equal to the matrix.
Okay, so those are important examples for us. Triangular matrices. So this is a great example of the use of the index notation here again. Like the fact that you can break a matrix up into these kind of matrix units, those kind of matrix units, those kind of matrix units, is the fact that you can break the matrix into the diagonal piece, and then like the upper and lower triangular pieces. I forget which is which without thinking through it, but yeah. And of course you can prove things like the product of upper triangular matrices is upper triangular, product of lower triangular matrices is lower triangular. So those actually form subalgebras of the matrix algebra. All right. let's go on here. And the proof of those things is straightforward if you use the lemma that I showed you before we took a break. Like basically it's just the lemma together with sorting through the indices. It's really just that. If you do that without that notation, if you just do it with big blocks of matrices, like you could still do it, but it's much more laborious. A nilpotent matrix is a matrix which is non-zero, and yet at some point it reaches its kth power becomes 0. Degree k means that k minus 1 is non-zero, but k is 0. So like, you know, this matrix here that I give in the example is nilpotent, I think, order 3, because the square is not 0, but the cube is. And nilpotent matrices are super nice because you can like derive formulas for their inverse through some like pretty simple algebra, you know. So like here's kind of a typical. Anyway, enough about that. Block matrices are important. So I have some things to say about that. I suppose we'll use those as we need them, but basically if you break a matrix into block, you can multiply block matrices as if the blocks are numbers, provided you keep the order of the blocks you can't just commute the blocks, of course, because those are matrix products, but otherwise it's pretty awesome. Like I can make this 4x4 matrix with a block of, you know, I've got a boost and a rotation here. Boost is a velocity transformation, rotation. And when I multiply these, I get, you know, products of boost with boost and rotation with rotation, which works like, anyway, so there's a fun physicsy example. This example here, I'm just facing the music of what does it take for this particular block matrix to be invertible, you know. That's kind of a fun example. All right, I'm getting too much into the weeds here. Let's go on. So the reason block matrices are interesting for numerical methods folks is that if you can write a matrix in terms of block multiplication, then it allows you to basically subdivide a large problem into a bunch of smaller problems. And since the computational complexity of problems depends typically on the square of the size of the problem, it's much nicer to have, you know, like 3 5x5 problems as opposed to, you know, 1 15x15 problem or something like that. Because 15 cubed is like way bigger than 5 cubed, even when you multiply it by 3. So that's kind of and that's one of the reasons that MATLAB is so beastly, is it makes robust use of block multiplication, and it has very natural language, programming language that it anticipates block multiplication. And anyway, don't ask me about that, I've forgotten it all. But but if I had a question, I know who to ask. Anyway, so I said we were going to get to examples. So here's some examples. All right. So let's just like try to understand the column correspondence property in these examples. That's really what I was after here with this projection. So let me zoom in so we can really see it. All right, so here's my original matrix, 1, 1, 1 minus 1. I do these row reductions. The reduced row echelon form of that matrix is 1, 0, 0, 1. What that means, so you look at this, right? Is there any linear dependence? There's not, right? Those are linearly independent. So if you row reduce the matrix such that the matrix becomes, every column in the row reduced matrix is a basis matrix, you know, a basis vector, then it's manifestly linear independent. So by the column correspondence property, these are also linearly independent, which of course is obvious because this is not a scalar multiple of that, right? But what's more interesting is that over here, if we look at all 3 two-dimensional vectors, you can easily, it's just, read it. The third column is the sum of the first 2. It's manifestly clear. If that's true for this, it's true for that. The third column is the sum of the first 2. That is the column correspondence property, and it's non-trivial. Let's look at some deeper examples of this. All right, so here's all this. Well, maybe let me just take a second here. No, the thing is, I'm talking about the column correspondence property with respect to the original matrix, and it's completely row reduced. It's Gaussian reduced, like the reduced to echelon form. The end of the road, the forward pass and the backward pass, all has happened for the Gaussian elimination. But it's true that you could do that same theorem I had written on the other board. You don't have to take the totality of all the elementary matrices. You could stop anywhere in the middle. So any column, in fact, what is the stronger statement of the column correspondence property is simply that when you do a row operation, any row equivalent matrix has all of the same linear dependencies between the columns as the original matrix. It's just that. Step by step, it's true. It's true for the first reduction, the second reduction. It's true for, it's just the reason we're interested in the last reduction is that when you get to the Gauss-Jordan eliminated, like the reduced row echelon form of the matrix, it's just so simple to read linear dependence amongst your columns. It's algorithmic, right? So, let's see here. See if I can find a bigger example. Now these are these notes I stole from my brother. I can tell because I never bothered with this notation, so I just ripped this off from my brother's handout. My middle brother William Cook works at Appalachian State. But so if we look at this original matrix, right? I don't know, what's the pattern between the columns? I don't see it right offhand, right? But if you look down here, what this shows you, first of all, it shows you that it is a fool's errand to try to write the fourth column as a linear combination of the first three. It's impossible. In fact, this is outside the span of these three, which means that this is an inconsistent system because that column is outside the column space of the coefficient matrix, which is to say that it's an inconsistent system. That's one thing I can say from this immediately. Also, of course, from the equation perspective, we have the equation 0x plus 0y plus 0z equals to 1, which is an absurdity. That's how we usually think of it. But you can think of it in terms of column space and spanning. It's healthier. It's more, that's a more mature viewpoint, right? That's the viewpoint I want for my students to have by the time they're done with linear algebra. I'm trying to get everything on here at once. Excuse me. All right, what else? So you tell me, Ernesto, can you see what else is true here? How about?
The third column is the sum of the first and second.
Right, the third column is the sum of the first and second. That should be true. Is it true? If we go back up to here, if we add these two, yeah. So you understand, this is very eye-opening. Once you see this, you don't always have to go through the equations corresponding to the system. You can just look at the row reduction matrix, and you can go directly from there to statements about linear dependencies and the columns. It's very freeing if you have the row reduction in front of you, right? If you don't have the row reduction in front of you, it always comes back, it all comes back to hand-to-hand combat if you don't have stuff worked out by the computer, right? But anyway. I talk about forward pass, the forward pass gets you to the so-called reduced echelon form, which means that you have identified your pivots, but there's non-zero things above. And then the backwards pass clears out the things above the pivot, and that the reduced row echelon form is unique. The reduced echelon form is not unique. All right, anyway. So, all right, so you get the idea? I can talk about another one here. One last one, and then we'll go on here. This one, if you look at it, so what do we see from this? We see the first three columns are linearly independent, right? And the fourth column is in the span of just the second and the third columns. So I can build, these two can build that. And kind of complicated way, you have to take half of the second one and 3/4 of the third one to get the fourth column, right? And then the fifth column, we can just get, well, that's just literally equal. You can just kind of see it, that is that, right? So, okie-duh. All right. Now, do you understand the algorithm for finding the inverse of a matrix?
Yeah.
Okay. All right. Well, I will not go over that then. I mean, you understand why it's true?
How I've gotten there.
Can you explain why it's true is really what I'm asking. I mean, I understand you know that you understand that if you want to find the inverse of a square matrix, you take the matrix, you concatenate it with the identity matrix, you row reduce that. If the matrix is actually invertible, the row reduction of the matrix will get the identity matrix in the left side, corresponding to the fact that the columns of the matrix were linearly independent, right? If you don't get the identity, that means the columns of the matrix were linearly dependent, which then what that means is that actually the homogeneous equation has a non-unique solution, which is tantamount to saying that the matrix is not invertible, right? Invertible matrices have linearly independent columns. Of course, it's interesting when the columns are not linearly independent, like, let's see if I have an example of that. Oh, well, that's a dumb example. Well, here's one, sort of. This is 3 equations in 5 unknowns, right? 3 equations in 5 unknowns. So you know you're not going to have a unique solution in that kind of situation, right? But this is like an important calculation to know. If I have 3 equations in 5 unknowns, I do the row reduction, right? What does this show me? It shows me that I can take the 4th and the 5th variables as parameters in the solution set, right? And the solution set, you can't, I mean, it's not quite, this is the one thing that requires a little bit of like post-processing past the matrix to actually find the basis for the null space, right? What's the basis for the null space of the matrix? Well, you have to look at these. X1 is equal to minus X4, X2 is this, X3 is that, right? And so if you put those in, and I use A for X4, I use B for X5 just to make it easier, I get this, right? And so once you see that, if you throw out the 0 and you just want, if you throw out the 1 rather, then you're looking at the null space calculation, right? So the basis for the null space would be like the span of -1, 1, 0, 1, 0, and 0, -1/2, 1/2, 0, 1, right? Like that's the, so you're good on the null space basis calculation?
Yeah.
Oh, okay.
Why does the same operation set turn the matrix into the identity matrix if it's invertible, turn the identity into the inverse? I know it does, but why?
But why is it true?
Why is that the case?
Yeah, let's look at that. Let's prove that. That's a good thing to go through. Let's do that. If I can find my markers again. All right, let's see here.
I understand that A turns into the identity because all the columns are independent, linearly independent.
Right.
And why?
Let's see here. I'm just. All right, so. All right, I think I can. So I mean, we could prove it for n dimensions, But I usually when I lecture it, I usually just do 3 because I feel like that's kind of like enough to not get like burdened, just overwhelmed with the process. So let's look at the proof in the n equals 3 case, because if you understand that, you can definitely do it for n. I mean for higher n, higher values. So let's think about what we're trying to, we're basically given A in F3 by 3, how to find the inverse, right? And here we've done the theory. A inverse A is equal to I, which is equal to A inverse, right? So like those are the defining conditions of the inverse matrix. And if you look at the notes there, I have a bunch of theorems that are true for it. But all right, so let's see here. So let's just study this. So we're trying to really, our goal is to find A inverse, which is equal to, let's say, V1, V2, V3, right? It basically boils down to that. We're trying to find these 3 column vectors, right? And so finding these 3 column vectors, did I get it?
Yeah.
Oh, yes, finally. Finding these 3 column vectors is our job. And all right, so you've got A times A inverse is equal to the identity matrix, right? What this is, though, is A times V1, V2, V3 equals to the identity matrix. The identity matrix is E1, E2, E3. And so what is this? Well, this is nothing more than AV1, AV2, AV3. Right? So what do we have? We have the equation AV1 equals to E1, AV2 equals to E2, AV3 equals to E3. We have these 3 systems of 3 equations and 3 unknowns. Right? So how do you solve these?
In a matrix.
Right. So to solve, let me call this number 1, 2, 3, and I won't try to, there's more. If I was super slick, I would dispense with this very quickly, but I'll try to be like a little bit less slick. So we look at the reducer echelon form of A with E1 concatenated, because E1 is the inhomogeneous term in the first system, right? 2, we look at we want to find what's the solution to this. 3, we want to find what's the solution to this. But here's the thing. In every one of these cases, they all share exactly the same coefficient matrix. So the same series of elementary row operations will bring it to the reduced row echelon form. And the counting says that that's it, because you've got 3 columns and then the 4th column doesn't meaningfully participate in the Gaussian elimination, right? Like if you're dealing with m rows, after you get to the mth pivot, you're done. You can't, there's no, well, that's not true, of course. If A is got a linear dependence, then the 4th column could be a pivot column. But anyway, my point to you is, if A is invertible, then there exists an elementary matrix E such that this is equal to what? E1A, and this is equal to, not E1, but just that's EA, right? Well, it's E times, it's not just A, it's E times A to A concatenated with E1, right? And this is that same elementary matrix. And this is that same elementary matrix, because it's the same row reduction in all three of these. Right? So, by the way, this is also equal to what? Well, but what does the row reduction have to work out to? In the case that A is invertible, by the other theory that I've developed in the notes there, it has to work out to the identity matrix, right? It has to work out the 3 by 3 identity matrix. And of course, it's the 3 by 3 identity matrix and the first column that we're looking for. That's what that was the solution. The solution to this is V1. V1's the solution. V2 is the solution to this one. V3 is the solution to this one. So if you put these together, right? If you put these together, you've got, that E times A with identity on it is equal to what? Well, EA times E, right, like that. But what else is it equal to? This is equal to E times A E1, A E2, A E3. And that's what? Oh, my bad. I'm sorry. I should. That's column 1 of A, column 2 of A, column 3 of A, right? Do I need to do that? Well, I mean, this is I can write this, right? That's an identity. This is, I'm just expressing A as these. And then I move the E in, and what's that give me? Right? EA, EA, EA. But, I'm sorry, I'm now confused myself. I'm so sorry. What's wrong with me? Yeah. I probably shouldn't have erased that. All right, so I take A concatenated with I multiply by the row reducing matrix, elementary matrix E, right? And so like this one, for example, is also equal to EA, EE3, right? Which is equal to this. Which means that EA is equal to I, and EE3 is equal to V3. Which is another way of saying that column 3 in the elementary matrix is in fact the third column of the matrix that we're trying to invert. Anyway, more to the point here, this is equal to what? This is equal to I, E. But you see this, right? Like I could, instead of just doing, I could put the J here, right? I could put, so we've got that and we've got that, right? But this just says that like column J of E is equal to Vj, which is to say that E is exactly the 3 column vectors we're looking for. But also you see that the row reduction, right? This is equal to the reduced to echelon form of the A concatenated with I. When I prove this in linear algebra, it comes out a little bit nicer because I've already done the legwork of showing how to solve multiple systems that have the same coefficient matrix at once, but it really goes back to the matrix multiplication column by column properties of the elementary matrix.
And so it's going to be A equals I, and then B has to be A.
That's right, that's right.
That makes sense.
Yeah, exactly. So this conclusion chart here is kind of nice. This just gives you I think you said you understand all this already, so that's good. Just for anybody's trying to follow along with us, if you basically read this chapter in my linear algebra notes, then you'll have a complete understanding of the material I teach in linear algebra for about the first 3 or 4 weeks. Something like that. Maybe, I guess it depends on the semester, but here. Look, this is, I love this theorem, the equivalent ways of looking at a, the equivalent ways of looking at an invertible matrix, right? A is invertible. The reduced to echelon form A is the identity matrix. Let's see what else. The homogeneous equation has only the zero solution. A is a product of elementary matrices. It's got a left inverse, it's got a right inverse. This is interesting because that's certainly not the case for function composition, right? You can have a left but not a right inverse for function composition. Not the case with matrix inverse. Of course, the thing we were just deriving this, right? The fact that you can solve any inhomogeneous problem for any choice of B, which is a fancy way of saying that the span of the columns of A form the totality of Fm. Well, let's say Fn here. But on the other hand, that there's a unique solution for any arbitrary B is also true. So this is some sense the surjectivity, this is in some sense the injectivity. So a linear transformation corresponding to such a matrix is a bijection on Rn. And then this transpose is invertible. That's something else. This transposition, this flip-flopping between row and columns, there's something interesting about that. But all right, so tomorrow we will jump into spans, linear independence, and so I think tomorrow I'm probably not doing this chapter, right? Because I think you know this stuff. I wanted to jump over to, let me go back to the start here. Matthew. Let's see here. Come on. All right, so we basically talked about chapter 2. We talked about chapter 3. I'm more or less skipping chapter 4 because the column correspondence property was really where it's at there. Determinants, I don't really have anything to tell you about determinants at the moment. The main thing is the determinant of the product is the product of the determinants. If you know that, wonderful. But we're going to find a way to derive that with wedge products later in this course, so let's wait for that. So next time we meet tomorrow, we'll be knee deep in vector spaces, and so we'll just keep pushing forward, and we'll be through this part of the course fairly quickly because I'm just going to keep charging ahead through the linear algebra. But I have been told by previous students who have not had my linear algebra that when I try to talk to them about deeper mathematics without having a discussion about linear algebra, there's something missing. So that it was useful for us to do this. Anyway, more tomorrow.